Hi, my name is MiryungKim. I'm a professor at UCLA. Today, I'm going to discuss the new trends of increasing hardware heterogeneity to support data-intensive computing and how our software engineering community could pioneer new ways of developer productivity tools. Some of you may know that I started research focusing on code clones, mining software repository, and refactoring. In other words, leveraging big code data and underlying systematic change patterns for improving developer productivity. Over the past 8 years, I have moved on to building software engineering tools for big data. And this motivated me to build automated debugging and testing for big data systems such as Apache Spark, and recognizing the importance of systems and runtimes. Today, I'm going to talk about the latest work on developer tools for hardware heterogeneity. Now we are seeing the new wave of opportunities that our software engineering community can contribute, such as automated refactoring, repair, and debugging and test generation in this new landscape of a heterogeneous hardware support for data-intensive computing. So you may be wondering, isn't there a dichotomy between software developer tools and hardware accelerator design? Why is this issue for software developers, not hardware design engineers? I hope I can convince you at the end of this talk that software developer tools and hardware heterogeneities are increasingly interconnected issues in this new rise of programmable hardware accelerators on major cloud services. So in the first 20 minutes, I'm going to discuss why heterogeneity now, what is the landscape of a heterogeneity landscape, and what are the implications of a heterogeneity. Then I'm going to showcase some examples of developer tools that my research group developed to target software engineers like you and me, not hardware design engineers. And I will share some exciting new opportunities and challenges that our software engineering community could contribute. So why heterogeneity now? Moore's original prediction in 1965 called for doubling in transistor density yearly. Although Moore's law held for many decades, shown on the left figure, it began to slow down sometime around 2000. And by 2018, it showed roughly 15-fold gap between Moore's prediction and current capability. Denial scaling states that as the transistor density increased, power consumption per transistor would drop. So the power per square millimeter of a silicon would be nearly constant. However, denial scaling began to slow significantly around 2006 and then faded to almost nothing by 2012. So when you think of a cloud and data centers, you often think of racks and racks of the same type of servers. And cost efficiency comes from leveraging the economy of scale of buying tens of thousands of the same machine. Managing a homogeneous system is also easier from the perspective of an operating system. So why change? The obvious reason is the slowdown of a technology scaling, aka the previous slide's reference to the end of Moore's law. If applications need more compute with energy efficiency, they need to look at special purpose hardware design. Many services also, such as a search engine, have a strict latency requirement. And the tail latency target of individual microservices, such as a search engine, are in the order of a millisecond. At the same time, we're entering this exciting era of a diverse spectrum of hardware accelerator that are being made offered on public cloud. So for example, Amazon F1 and AWS or Intel's like FPGA developer cloud provides this kinds of FPGA-based acceleration capability. Also, expensive hardware such as supercomputers or quantum computers are being offered as a public cloud service as well. And this value proposition is very attractive for both the developers and end users. You could pay as you go. There's no need to buy an expensive hardware. So what does heterogeneity look like? RISC-based CPU, the main advantage of a CPU is that it is easy to program them and supports any programming framework. GPU are specialized processing units that are mainly designed to process images and videos. And GPUs are programmed in CUDA and OpenCL and provide thus limited flexibility compared to CPU. In the past, FPGA used to be a configurable chip to implement glue logic or custom functions. However, FPGA have been emerged as a very powerful processing unit that can be reprogrammed to enable low cost and low power consumption. ASIC is an application-specific integrated circuit. Its design cycle is long, so it's impractical to spin up ASIC for each and every evolving application. In the next few slides, let me talk about an example of FPGA and ASIC. So FPGA is a field programmable gate array. It has a programmable logics, programmable interconnects, customizable building blocks, block random access memory, DRAM, and digital signal processing unit, DSP. There's no need to go through a lengthy fabrication process when you work with FPGA. Microsoft Bing search engine utilized FPGA-enabled servers to achieve 50% throughput and 25% tail latency reduction without increasing power consumption. This is a remarkable acceleration. However, programming with FPGA is not easy. It is often programmed at the level of a register transfer level hardware description languages such as Verilog and VHDL. Let's consider an example of an application-specific integrated circuit, ASIC. ASIC could provide higher performance than FPGA. An example is Google's TPU, TensorFlow Processing Unit. TPUs are very fast at performing dense vector and matrix computation and are specialized for running applications based on TensorFlow and deep learning. However, ASIC design cycle is very long. Its custom fabrication requires almost like 6 months and 2 years. And it is also costly in terms of design. According to McKinsey, 7 nanometer ASIC development is now reaching almost 300 million. So what are the implications of a heterogeneity? Hardware design is typically done using a register transfer level, or RTL, hardware description languages such as Verilog and VHDL. Most software programmers are unfamiliar with these languages such as Verilog or VHDL. And according to 2020 US Bureau of Labor Statistics data, there are over 1.8 million software developers in the United States, but fewer than 70,000 hardware engineers are available. So FPGA and hardware design have been around for a while. In particular, FPGA has been around since the 80s. Programming FPGA using hardware description languages require reasoning about computation at a very low level of abstraction. So to raise this abstraction level of hardware design from hardware description languages to higher level languages such as C or C++, high-level synthesis technology were developed. So this HLS promises to make circuit design more accessible as it can automatically compile computation kernels written in C or C++ into an RTL level description. So in this keynote, We will in particular focus on FPGA as a key target area of a heterogeneity landscape for software developers, as FPGA is reprogrammable. And HLS can also raise the abstraction level of FPGA design. So therefore, in the next slides, let me describe the developer workflow with the high-level synthesis for FPGA in more details. So first, let me describe the traditional FPGA design flow. A hardware engineer profiles an application code, in this case, like KNN, and once she identifies a time-consuming hard code computation path, she will separate this kernel code, shown in blue, from a host application code. Then she writes this computational logic directly in hardware description languages like Verilog or VHDL. It eventually produces gate-level bit streams through RTL synthesis process by going through steps such as gate-level synthesis, routing, and timing validation. And once the FPGA-based hardware accelerator is available, then host application code running on CPU makes an invocation to a hardware accelerator. Let me now describe HLS-based hardware design flow. So to raise the abstraction level of FPGA design from RTL languages to languages such as C and C++, high-level synthesis, HLS compiler translates input programs written in C or C++ code into an RTL. Now, let's consider the tool usage latency from an engineer's perspective. As you know, GCC compilation and execution of a C is typically in the order of a second. It's very fast. However, HLS compilation shown in red is much longer than GCC like C compilation. Due to the process of resource allocation, scheduling, and bindings in HLS, it generally takes the order of a minute to hours. RTL synthesis, which is like, in other words, baking hardware circuit, shown on green, is expensive process also in the order of hours or days. Therefore, before committing to proceed with RTL synthesis, HLS developers use C and RTL co-simulation tool to perform cycle-accurate HLS simulation. HLS simulation shown in oranges also long in the order of minutes and hours. So consider this KNN example again. In order to achieve 7x speed up on FPGA, it may take several days or even a month. It is because each HLS compilation and co-simulation are in the order of 10 minutes or long. And also, developer must repeat this process of a manual code rewriting numerous times in order to achieve a performance boost. So this could be easily, weeks of engineer's time. So even though HLS raises the abstraction level from RTL languages to C and C++, programming with the HLS-C is not easy for software developers. In fact, HLS-C is a dialect of a C, not regular C and C++. The quality of a circuit generated by HLS tools depends heavily on the structure of an input C and C++ code program and the hardware implementation code, so-called pragmas, provided by hardware design engineers. This requires engineers to have a microarchitectural expertise. Engineers must know how to partition the data array to map onto the on-chip memory blocks, how to parallelize and pipeline the computation. Most software engineers, like you and me, do not know how to perform these hardware-specific optimizations. next 3 slides, I will show the concrete example to illustrate why HLS rewriting is a non-trivial task. HLS requires specifying a bit width for each data type to save storage and optimize computation. So instead of using default 32-bit on CPU, HLS uses arbitrary bit width. So for example, one can use a 7-bit integer for her program. Similarly, developers must tune the precision of a floating point numbers and computation. So instead of using the default 8-bit exponent and 23-bit mantissa for 32-bit floating point, developers have a flexibility to tune precision for memory saving. And in hardware, all resources are finite resources. So therefore, the use of recursions, pointers, dynamic memory allocation with a malloc and free, which is a standard in C, is not available either. So developer must rewrite program to remove or re-express the use of a dynamic data structure, such as a linked list or a binary search tree. And most importantly, performance boost is not automatic with the HLS. It requires a painstaking rewriting iteration to get the performance boost. So consider this a 7-line convolutional neural network example of a single layer. An existing commercial HLS tool generates an FPGA-based accelerator initially more than 100 times slower than single-core CPU. And in order to get the performance boost, you need to properly restructure the input C code to tile the computation. This requires inserting 28 pragmas, so-called like design hint for hardware implementation. Then the final FPGA accelerator is almost 90 times faster than single-core CPU. In fact, according to Xilinx's survey, less than 5% of the software developers are able to make use of a heterogeneous, only 5%. So now let me describe a few examples of a developer tools that my research group developed to target software engineers like you and me, who may not have a hardware microprocessor expertise. And especially in the domain of a test generation and automated repair. So the first problem we worked on is automated test input generation to enable efficient differential testing between CPU and FPGA. So when you port C code to FPGA-based accelerator, heterogeneous computing application can produce a different result on FPGA compared to CPU due to various platform-dependent characteristics, such as bit width, available resources, memory accesses, recursion depth, and data flow mode. So consider this example of a computing gradient vector of input images by taking absolute distance between 2 adjacent pixels. Because an optimized FPGA kernel uses a custom bit width for integers and floating point, it could lead to overflows on FPGA. Worse, it could still crash or produce a wrong output silently when the kernel is executed on FPGA accelerator. So for example, on this input that you see over here, it will produce a wrong output 1 instead of 257. Thus, detecting platform-dependent divergent behavior is very important while you are designing hardware accelerator and or writing heterogeneous computing application where kernel code is executed on FPGA. So you may be wondering, is a fuzz testing applicable to the problem of finding divergence error between CPU and FPGA? Fuzz testing has been around for a long time. since Bartomillo tried this concept of iterating, mutating input and repetitively invoking a target subject program to induce a failure almost 30 years ago. Gray box fuzzing monitors execution feedbacks such as a branch coverage in order to prioritize inputs leading to new behavior. So my postdoc Chen measured the running time of AFL on the CPU and to find the CPU and FPGA divergence errors. These errors are reported on Xilinx forum, and we try to apply AFL. And it would take at times 93 hours, over 4 days of a fuzzing time to find a single error. Why? Let me describe 3 technical challenges that will make AFL-like technique not easily applicable in the HLS and FPGA domain. First, gray box fuzzing typically uses branch coverage as a feedback. Branch is implemented using various mechanisms in the hardware, such as MUX, and they are not very meaningful at the gate level. So even if you could inject the branch coverage signals to hardware, they may not be meaningful signals for finding divergence error between CPU and FPGA. Second, typical input mutations such as a bit level or byte level mutations are unlikely to be effective in stretching hardware behavior in terms of a finitized resource usages. And third, as you know, fuzzing assumes that program under test can execute very quickly in the order of milliseconds, like say, making invocations of more than 1 million times per minute. On the other hand, HLS simulation takes in the order of 10 minutes or hours. So this long simulation time makes the fuzzing-like technique prohibitively expensive. So we address these 3 challenges by designing new fuzzing feedback guidance called hardware accelerator spectra monitoring. This technique uses both static analysis of a hardware design hint, so-called pragma, and dynamic analysis to monitor hardware accelerator behavior. And we use this idea of accelerator spectra monitoring to also adapt to new input mutation strategy and to invoke HLS simulation in a selective manner. So let me talk about the most important optimization called the accelerator spectra monitoring, which designs a new fuzzing guidance signal for FPGA accelerator. So what we do is that we statically analyze HLS pragmas inserted in a kernel code. And based on these design hints, we design new monitors that are important for monitoring hardware accelerator behavior. These monitors could be a value range for each element in the array or the Scala variable, how much size of a finite resource is currently used, how many times a loop execute, and these are all important behavior characteristics for hardware acceleration. Then we inject these monitors at the boundary of a host and kernel code. So in this example, accumulate is a kernel function which is invoked from host code or application code. And this new accelerator spectrum monitoring also enables 2 important optimizations, where we can invoke HLS simulator only if the newly generated input is likely to stretch FPGA execution behavior. And we can also adjust the activation probability of an individual input mutation operator so that we could push input mutation towards the direction of a stretching FPGA behavior. So by all these optimization, we actually found that we can make more than half of a generated input that could be inducing divergent behavior between CPU and FPGA for differential testing. And we could speed up the testing time almost 17x by adjusting activation probability of an individual input mutation operator. We can also save time almost by 9x with the selective HLS invocation. And with all this together, we could achieve 750x speed up compared to naive AFL like fuzzing. This means over 4 days of fuzzing time in our motivating example, which took more than 90 hours, can be reduced to 7 to 10 minutes to find CPU and FPGA divergence error. Now, let me discuss the Heterogeneous, which adapts automated software repair to translate C to C++ program to HLSC fully automatically in order to help the programming barrier of programming in the HLSC. Heterogeneous is also an optimizer because what we are doing is that we are applying behavior preserving transformation, but also ensures that the updated code has a superior performance than the original version. So in the software engineering community, we had search-based evolutionary repair for a while. It uses test successes as a fitness function, and it iterability mutates program towards the direction of a test successes. So can we consider this paradigm of automated search-based repair to automate HLS compatibility edit or HLSC compatible rewriting? Can we use this technique so that we could simultaneously reduce the number of compatibility errors, but also improve the performance? And it turns out that it's extremely difficult to adapt search-based repair to heterogeneous computing application domain in a straightforward manner. There are 2 reasons. First, HLS compilation and simulation takes a much longer time compared to CPU compilation and execution. Second, the HLS compatible edits require complex restructuring and multiple coordinated edits. So the repair edit search space is very large. So for example, GenProg reports 0.2 seconds for each repair trial. However, HLS for our previous example would take 14 minutes for compilation and simulation. So we designed Heterogeneous with several optimizations to address these 2 technical challenges. And then in the next 3 slides, I will discuss 3 of those optimizations with more detail. First, we recognize that HLS repairs are complex, yet they have a recurring pattern. So my postdoc Chien, my graduate student Jian, and I studied 100 posts in the Xilinx forum for HLS. You could think of it as a Stack Overflow for HLS to study how HLS compatibility errors could be fixed through rewriting. We then encoded these edits as an edit recipe. These edit recipes are implemented as a parameterized LLVM level, like Clang AST transformation. So each of the 5 error categories, we defined about 5 to 10 edit recipes. Each edit recipe consists of about 1 to 10 AST node and insert and delete. So there are about 40 recipes in total. And all recipes except the top function categories are designed to improve performance, but also ensure hardware synthesizability. And we noticed that these edits are not only parameterized, but they have a precedent or prerequisite relationship or dependence relationship. So we leverage these prerequisite relations to prune the search space of a repair edit. So for example, while we are enumerating, we understand these dependencies, so that will reduce the search space while we're enumerating edit space. And this also increases the chance of constructing valid edit. And the last optimization, early candidate rejection, is used to skip the expensive HLS compilation if a repair does not conform to HLS coding style. So for example, we can reduce the time from 14 minutes to 1 second with our LLVM front-end checking, like our custom linting technology, without invoking the full HLS compilation. If HLS pragma, such as a HLS unroll that's seen over there, appears within the loop body, where it should appear outside of the body. So on the evaluation with HLS benchmark, Heterogeneous successfully produced a HLS compatible version for 9 out of 10 subjects on the 3-hour time budget. We could automate complex edit, and these edits reaching almost 438 lines of change. And our dependency-based search achieves almost 35x speed up compared to a random search process. And as also a side benefit, Heterogen provides these automatically generated tests to enable automated repair, which has a much higher code coverage than what was provided by the HLS benchmark. And also on average, these heterogeneous converted versions are 1.6x faster than original CPU version. And manually crafted HLS versions are about 2.4x faster than the original CPU version, but it would require a lot of hand manual code rewriting. So we're providing all this benefit of a performance boost with the full automation of HLS rewriting on the 3-hour time budget. So now I would like to describe open problems that our software engineering community can contribute. In this new era of data-intensive computing with the hardware heterogeneity, I hope you can join me together in building software developer tools that can democratize custom hardware acceleration to regular software engineers. So this lack of programmability is a long-standing problem in hardware design. And this issue is now being addressed with the development of a new DSL in higher level languages. So for example, HeteroCL is a Python language front end to HLS. And Headlight is a new DSL for image processing. Also, there's more movement of having like API or a library to target multiple platforms. So Intel's one API is a data parallel C++ library based on SQL specification that can target multiple platforms such as a GPU and multiple versions of FPGA. Department of Energy Iris runtime from Oak Ridge National Lab is another kind of a work that is like targeting multiple heterogeneous programming system. So this provides exciting new opportunities to ease migration to new API or new DSL. We could imagine providing automated refactoring or automated code hint for this pragma generation. However, there are 2 technical challenges exist. First, we have a fewer code examples in this domain than regular Python, Java, C++ domain. Another challenge is that we must sometimes trade off accuracy and performance for something like a machine learning application. So for example, floating point computation could be tuned for speed up while sacrificing numerical accuracy. Next challenge and opportunity lies on the domain of debuggability. Debugging is a hard problem, both in software engineering, but also hardware design. And yet, effective root cause analysis and debugging is necessary. So far, this debugging support has been somewhat separated via hardware level like in-circuit debugging. There are also HLS debuggings available, which injects some instrumentation signals through source-to-source transformation. As you know, in our community, there have been a variety of software monitoring and tracing techniques for debugging for runtime verification, including taint analysis, and many kinds of custom monitors and monitoring strategy. Now is the time that we can create more effective and efficient debuggability support by mixing software monitoring with the hardware probes. The challenge is that injecting hardware probe is difficult. It also poses a computation time overhead. And since this is time for injecting hardware signal, which is sort of modification of a hardware design, is also long. Next, in our community, and in particular, this community of ISTA is really about software testing and analysis. And there have been major streams of automated tester generation techniques, such as fuzzing and gray box fuzzing, symbolic execution, and search-based text input generation. These are all compute-intensive exploration problems. So to expedite these test input generation, we could consider hardware acceleration for test generation. Vice versa, we can also design new methodologies and new optimizations to target heterogeneous computing application by analyzing and understanding the characteristic of a hardware acceleration. So for example, we could design new input mutations, new search strategies, or new fuzzing guidance signal at the directly, perhaps at a hardware level, to test the heterogeneity more effectively. Lastly, the current context is that hardware heterogeneity is increasingly supported through deep layer of a compilation flow. So for example, Headlight and HeteroCL compile to HLSC, which gets compiled down to RTL before the hardware synthesis. Furthermore, with the rise of LLVM MLIR, compiler developers can declare new dialects and extend the existing compiler IR, internal representations, easily. Therefore, to test this increasingly complex layered compilation flow, we need new techniques for input program generation. The challenge here is that the search space of compilation parameters and hardware design hints is extremely large. So we need to be very intelligent about these testing, search space of testing. So with that, I would like to thank my students and collaborators. They taught me and supported me in this new direction of a software developer tools for hardware heterogeneity and data-intensive computing. I hope you could join me and others in this new exciting direction of a hardware heterogeneity and data-intensive computing. And lastly, I would like to thank my funding sponsors, National Science Foundation, Intel, and ONR. My group's research projects are available as open source on our GitHub, so please check out this URL to find more details about our project. So with that, now I'll take your questions.